Steinhauer here. Welcome back. We're continuing our discussion of light and how we can determine things about the universe and objects in the universe based on the light that we get from those sources. So today we're going to talk about the Doppler effect. The Doppler effect is extremely important for measuring relative velocities of things in space. And you're probably familiar with the Doppler effect at some level because we experience it. We experience the Doppler effect with sound in our everyday lives. If objects are moving towards us, we hear them at a different pitch than if that same object emitting a sound is moving away from us. And that's because the wavelengths of an approaching object gets compressed and the wavelengths of a receding object get stretched out, and we hear that change in wavelength or that change in frequency, because the wave speed is the same, as a change in pitch. So there's a nice video about Neil deGrasse Tyson, which demonstrates this for NASCAR, linked below. Take a look at that. And this animation is also linked. And this animation is good for understanding why this works, right? So we've got an object here, and this could be emitting light waves or sound waves. Doesn't really matter. All these waves basically work the same. And so the way this works is this particular wave is traveling through a medium, and you're going to watch as this object moves to the right, it's going to emit a wave, and that wave is going to spread out in a spherically symmetric distribution and way. And the wave itself is not going to be the center of the wave is not going to be moving. In other words, you're going to see a circle expanding, and the center of that circle is going to stay at the same spot. So this wave that we're seeing here at the beginning was emitted when this object was about right there, and so it's going to continue spreading out uniformly from the place where it was emitted, which is right here. Now, the way the Doppler effect works is the next time this object emits the next crest of the wave anyway, 1 second later, because I've got a frequency of 1 hertz here, the next wave that gets generated will be shifted over a little bit to the right, and that center will continue to expand. And you're going to see what happens. If I play this, keep an eye on every one of these circles, right? They're expanding, but they're expanding from a center point that's slightly different as this object moves. And I want you to see what happens. As these waves progress, you can consider this a single propagating wave outwards, and maybe this is the trough of the peak of one wave and the peak of the next wave and the peak of the next wave and the peak of the next wave. You're going to experience, so somebody standing over on this side of the box will experience those waves traveling towards it, right? And so that person can measure the wavelength of that wave as it comes along, right? And they will measure some number for it. Somebody standing over here will do the same thing and measure the waves as they come along. And they'll measure different wavelengths for that wave, right? The person in the direction of the line of travel will see the wavelengths get shorter, and the person who is opposite the direction of travel will see those wavelengths get stretched out and get longer. And that's simply because the object is moving, but the center of these expanding circles is not moving. It is staying at the same place. You can see this a little bit better if I make the speed a little bit higher. If I go up to 0.5, I can replay this. And the faster we go relative to the sound speed, which is C, relative to the wave speed, which is C, the more this effect is important. And the more this effect stretches out the waves in one direction and compresses them in the other. If I go to something like 0.8, now this thing's really moving, and it's really piling up these waves, and it's really stretching out these waves on the other side. It's probably not obvious here, but it's also true that if you look perfectly perpendicular to the line of sight, these waves are exactly the same distance apart as you would expect them to be if the object was stationary. Interestingly, this doesn't work for the speed of light. You can't go at or faster than the speed of light, but you can go at the speed of sound. If you want to know what a sonic boom is, set this to 1 and replay this, and you'll see what happens. Now, this object is traveling at exactly the same speed as the waves are traveling, and you see what happens to all of those waves. They just keep piling up along this front, and this creates kind of a shock wave. And if you've ever heard the term sonic boom, when an object approaches and crosses the sound barrier, it generates a sonic boom, and that's exactly what happened. All of those sound waves from that object get compressed, And if you're getting them from an object, and even if you're not right in the line of sight of that object, you will receive all of them at once. And you will hear a deafening noise as that wave passes by you, because all of them have been lined up on exactly the same point. That's what a sonic boom is. It's just a manifestation of the Doppler effect when you happen to be going exactly the speed of light, at the speed of sound. That's not possible for light, but you can get pretty close to the speed of light. Let's replay this. So you may have an equivalent of almost a sonic light flash or something if you were in the direction of motion. Certainly, there is an effect where if you're going close to the speed of light, objects tend to look brighter in this direction and fainter in this direction. It's just the way this wave seems to be propagating outwards. Anyway, that's neither here nor there. The Doppler effect is what's important. You can tell an object and whether it's moving towards or away from you and how fast it's moving towards or away from you based solely on what the wavelength of that light is compared to what you expect it to be. Okay, you can play with that if you. Here is a diagram from your book showing exactly the same phenomenon, but I think it's easier to see it in the animation than it is in just a static picture. Here you see a stationary object and you see these wave crests expanding outwards equally in all directions. Everybody's seeing the same wavelength for this thing in all directions. If the object's moving, though, this original wave crest was emitted at the center, and then the next one, and the next one, and the next one. And so the wavelengths as the object moves towards the bottom of the screen get shorter in that direction, and they get longer in the other direction. And in the perpendicular direction, interestingly, they're not changed at all. So that's the basics. That's the why of the Doppler effect. Of course, we need an equation if we want to quantify any of this. And here is the equation for the Doppler effect. The radial velocity divided by c, we'll talk about what we mean by radial velocity because it's different than regular velocity, is equal to lambda obs minus lambda rest divided by lambda rest. So let's just define all of those terms real quick. Vrad, of course, is the radial velocity. And what we mean by radial velocity as opposed to another velocity is simply it is the velocity along our line of sight, along your line of sight, along the observer's line of sight. So it is only the component of the velocity that's along the line of sight. Let's put some units here. Obviously, velocity is anything that has meters per second or kilometers per second or miles per hour or anything like that. Typically for, we'll do meters per second, but often you'll see kilometers per second because things tend to be moving fast in space. Okay, lambda obs is the wavelength of some feature observed in the object. This typically is nanometers, but any length distance will do. Lambda rest is the wavelength that you expect that feature to be at if the object were at rest relative to you. And that will also be in nanometers. And of course, c is the wave speed in the case of, we're always going to be talking about light being Doppler shifted. In the case of light, this is the speed of light. And of course, this also has units of meters per second. Okay, let's try this out. So we've already seen some hydrogen lines, and we know that there are some specific absorption lines or emission lines that you'll get from hydrogen, and we happen to know the rest wavelength of those particular lines, right? We know where they should appear. We know in our lab, sometimes you'll see lambda rest instead of as lambda lab, and what lambda lab means is if you had a hydrogen spectrum in your laboratory and it's not moving with respect to you because it's fixed to your lab table or something, that's the wavelength that you would see for it. So the hardest part of this equation is always going to be which is lambda obs and which is lambda rest. Lambda rest is always the one that you would expect it to be at if that object were not moving. Lambda obs is always the one that you're observing in the object that you're trying to figure out how fast it's moving with respect to yourself. So a hydrogen line is measured in the lab at 656 nanometers and observed in a star at 650 nanometers. What is the radial velocity of the star? Okay, let's write down our equation. We know that V rad over C, lambda obs minus lambda rest divided by lambda rest. Again, let's write down all of these things that we know. We know what C is, it's the speed of light. We'll get to that in a second. But which is lambda obs and which is lambda rest? This is the most important thing now. Make a guess, and we'll see if you're right. Lambda rest in this case has to be the rest wavelength of the hydrogen line. That wavelength at which we would expect it to be at if the object were not moving. And that's 656 nanometers. Lambda obs is the wavelength that we see it in the star that we're trying to measure the radial velocity of, and that would be 650 nanometers. Now, you might think we're going to plug in C in meters per second, that we need to convert these to meters, but we really don't. As long as we use the same unit for all of these wavelengths, we'll get the same unit on top and bottom, and we will divide the two, and we will, and that unit will cancel out. And then radial velocity will just be in whatever units we plug in for C. So we don't have to worry even about, in this case, converting the units. Okay, let's plug them in and see what we get. Lambda obs is 650 nanometers minus lambda rest is 656 nanometers divided by lambda rest, 656 nanometers. Let's do the subtraction first. 650 minus 656 is negative 6 nanometers on top divided by 656 nanometers on the bottom. Divide negative 6 by 6 and you get, but negative 6 by 656, and you get negative 0.0092 or so. Now, what are the units on this number? We just mentioned it. You're dividing nanometers by nanometers, so they actually go away. This is a unitless number, right? And what is this equal to? We stopped writing this over here, but this is still V rad over C. What is this number? Sometimes this is all you care about. Sometimes I'll ask you, what fraction of the speed of light is this star moving? And this is the answer to that question. 9.009, or a little less than 1% the speed of light, right? Sometimes, because that's what V rad over C, it's the fraction of the speed of light. Sometimes I'll ask you to multiply both sides by C and actually get a number that has units. So let's go ahead and do that. If we multiply both sides by C, we get the C's canceling out on this side, and we get V rad by itself over here. And over here, we get negative 0.90092 times the speed of light, which we know is 3 times 10 to the 8 meters per second. And if you multiply those two numbers together, you get a number that is negative 2.7 times 10 to the 6 meters per second. Or if you'd like to convert this to kilometers, just divide by 1,000, negative 2,700 kilometers per second. That's a really big number. This thing's moving fast, right? 2,700 kilometers per second. 2,700 kilometers will get you, to the middle of the country in 1 second. So this star is moving really fast. And you'll notice its wavelength hasn't shifted that much, 6 nanometers out of 656. So this is, because the speed of light is so fast, how much it shifts is proportional to the fraction of the speed of light that object is moving. Objects have to be getting substantially close to the speed of light for you to be able to have any sort of measurable effect going on with these lines. That's the one thing. The other thing I want you to point out is what this negative sign means. That's important. The negative sign is a convention but you need to know what that convention is. The convention is, if the radial velocity is negative, that object is moving towards you. If the radial velocity is positive, that object is moving away from you, right? This makes sense. You should be able to see just from the fact that the 656 has gone to 650. The fact that it's moved towards shorter wavelengths means that that object has to be moving towards you. If you don't believe me, do that animation and play with it until you get this, until you have the concept down. Objects are moving towards you, their wavelengths get shorter. Objects that are moving away from you, their wavelengths get longer. So you should have been able to tell, even before you plugged in any numbers, that this star is moving towards you simply because the wavelength has gotten smaller. This negative sign also means that the wavelength has gotten shorter and that object is moving towards you. Positive is away, negative is towards. Okay, so if you're looking at how does this work in practice? In practice, you actually see a spectrum, right? You see maybe emission lines, maybe some absorption lines, and maybe there's some pattern. Maybe this is the hydrogen spectrum, and you've got a red line and a teal line and a blue line, right? And you know from your laboratory work with hydrogen where those lines should be if that object were at rest relative to you. And so you can see, well, just by looking at the spectrum, this object 1 must be moving away from you. And this object 2 must be moving away from you even faster because all of those lines have been shifted to the right. And here, this object must be moving towards you because all the lines have been shifted to the left with respect to the stationary object. And here, this object must be moving towards you even faster because they've been shifted to the left. This is another, there's another name for all of this. Because all of these lines, look at these spectra right here. All of these lines have been shifted towards longer wavelengths, every single one of them. And since the red is at the long end of the visible part of the spectrum, we call this a redshift. Anytime an object is moving away from you, all of those lines get shifted towards longer wavelengths, towards the red part of the visible part of the spectrum, and so we call that a redshift. And you can imagine, since blue is on the other end, we call these a blue shift. So if an object's moving away from you, its lines will be shifted towards longer wavelengths. It will have a positive radial velocity, and we'll call that a redshift. If an object is moving towards you, all of its lines will be shifted towards shorter wavelengths. It will have a negative radial velocity, and we call that a blue shift. Those are things to know. Okay, I mentioned this before, but it's important. And the radial velocity is only a measure, and Doppler shift only tells you about motion that's directly along your line of sight. So for instance, this object will see the entire velocity, object 1 will see the entire velocity because it happens to be moving along our line of sight. Object 2 has a non-zero radial velocity, right? But it's moving perfectly perpendicular to the line of sight from the Earth. And so we will measure a radial velocity of this object as 0, right? The component of this vector, this line, that's along our line of sight is nothing. It doesn't point towards or away. If you've got some object like 3 that points kind of as most objects do, oriented in some random manner, it is the component of that velocity that is along our line of sight that we will measure. We will measure a positive radial velocity, and it will be that much, which is not the true velocity of this object. This object is moving faster than this, but it is the radial velocity. It's the component of that velocity that's along our line of sight. We'll measure a positive radial velocity for this object because it's moving away from us, and it will be less than the true velocity. We can't tell from the Doppler shift that there's a component in this direction as well. But the Doppler shift does tell us whether it's generally moving towards us or away from us. So here's a review question for you. Make sure you understand this. Here we have an observer over here. here we have an object, and this black line shows the true velocity of this object through space, and it's moving at 5 kilometers per second. I have broken this up into this component and this component, and I want to know, what will the radial velocity of this object be as measured by this observer? Go ahead and write down an answer. Okay, we're back. What is the answer? Well, again, this object will be the Doppler shift will be important. It will be in effect. And since the component of this object's velocity, it's along the line of sight, points in this direction, that's towards the observer. So it's going to be, the lines will be blue shifted. How much? It will be moving exactly 3 kilometers per second towards us. And so that's the radial velocity. And so we will measure a radial velocity, in this case, VRAD, will be -3 kilometers per second. Okay, that's all for Doppler shift. Do play around with the animation some, and we'll come back in the next video and talk about how we can get the temperatures of objects based on how much light we're getting from them.